After studying this module, you shall be able to learn symmetry elements and symmetry operations. Know various symmetry elements and symmetry operations. Identify symmetry groups. Evaluate symmetry groups of some metal carbonyls. Understand application of IR spectroscopy in the determination of symmetry of metal carbonyls.
In this module, we will study about the application of infrared spectroscopy in determination of symmetry of metal carbonyls. We will understand the role of symmetry elements and symmetry operations. Various symmetry elements and symmetry operations contain symmetry, which can be explained as an observer who closes his eyes during the operation will not perceive any change in the geometry and physics of the molecule. Then next is symmetry elements. You are already aware that a symmetry element is a geometrical entity, that is, an entity which is related to geometry such as number 1 a point, a number 2 a line, or number 3 a plane. This can help in carrying one or more symmetry operations. You are also aware about the symmetry operations. Symmetry operation is defined as an action that leaves a molecule looking the same after it has been carried out. Let's study various symmetry elements and operations in detail. There are 5 kinds of symmetry operations and corresponding 5 kinds of symmetry elements, which includes identity denoted by E, and the entire object or identify is the symmetry element. Rotation denoted by Cn and proper axis of symmetry is the symmetry element. Reflection denoted by sigma, here plane of symmetry is the symmetry element. Inversion denoted by I and center of symmetry is the symmetry element. Improper rotation by Sn, here the improper axis of rotation is the symmetry element. After becoming familiar with the various symmetry elements and operations, we will apply this knowledge on some metal carbonyls. It is often possible to predict the symmetry of the arrangement of the carbonyl groups around the metal atom in a metal carbonyl from the number of carbonyl stretching bands that are observed in the infrared spectrum. However, this task requires the adequate amount of judgment and proper experience in order to avoid the errors. This procedure consists of 3 steps. Number 1, several possible structures of metal carbonyl under consideration are drawn. Number 2, the number of carbonyl stretching bands which are expected to appear in the IR spectrum is calculated from the symmetry of each structure with the help of physical and mathematical requirements. Number 3, the experimental observations are then compared with the above predictions. The structure which disagree with the experimental observations are discarded. In favorable circumstances, there will be only one structure remaining. Let's try to understand about this topic with the help of some graphics and visuals.
So now we will study about symmetry elements and symmetry operations, and these will divided into first symmetry, second, symmetry elements, and third, symmetry operations. Now, first is symmetry. Any molecule is said to have symmetry if any real or imaginary operations of rotation or reflection, when carried out on the molecule, lead to a new orientation which is indistinguishable from the initial one. In other words, an observer who closes his eyes during the operation will not perceive any change in the geometry and physics of the molecule. For example, when CO2 molecule is rotated about x-axis by an angle of 180 degree, the new orientation obtained is indistinguishable from the initial one, as shown in the following figure. Therefore, we can say that the CO2 molecule has symmetry. Symmetry is a widely distributed property in the nature. For example, human body is symmetrical. Its left hand Its left-hand side is the mirror image of the right-hand side. Some more examples of symmetry in nature are illustrated in the figures shown. Its left-hand side is the mirror image of the right-hand side. Some more examples of symmetry in nature are illustrated in the figures shown. Some molecules are more symmetrical, that is, have high symmetry, while some other molecules are less symmetrical, that is, have low symmetry. For example, boron trichloride molecule is more symmetrical than ammonia molecule. It has been illustrated in the following figure. Slide 11. Next, we will study symmetry elements. A symmetry element is a geometrical entity, that is, an entity which is related to geometry such as a line, a point, a plane about which one or more symmetry operations can be carried out. Now, we will study about symmetry operation. A symmetry operation is a movement of a molecule or a body about any symmetry element in such a way that the orientations of the molecule before and after the movement are equivalent or indistinguishable. A symmetry operation can also be defined as an action that leaves a molecule looking the same after it has been carried out. Let us illustrate it with the help of the following examples. 1 and 2 are indistinguishable orientations. Therefore, the rotation of BCl3 molecule about the z-axis by 120 degree is a symmetry operation. On the other hand, 1 and 3 are distinguishable orientations, and therefore the rotation of BCl3 molecule about z-axis by 60 degree is not a symmetry operation. Now we will study various symmetry elements and operations. There are 5 kinds of symmetry operations and corresponding 5 kinds of symmetry elements as given in the following table. First, identity denoted by E. In this, the entire object or identity is the symmetry element. Second, rotation denoted by Cn. In this, proper axis of symmetry is the symmetry element. Third, reflection denoted by sigma. In this, plane of symmetry is the symmetry element. Fourth, inversion denoted by I. In this, center of symmetry is the symmetry element. Fifth, improper rotation by Sn. Improper axis of rotation is the symmetry element. In various symmetry operations, first is identity operation or identity element of symmetry. The symmetry operation which leads to the production of an orientation which is identical to the original one is called an identity operation. Because every molecule is indistinguishable to itself if nothing is done upon to it. Every molecule possesses at least identity element of symmetry. Thus, identity operation can be carried out in all the molecules. It is denoted by the symbol E. Next is plane of symmetry or reflection operation. If the reflection of all the atoms of a molecule through a plane passing through the molecule yields an orientation which is indistinguishable from the initial one, it is known as reflection operation, and the plane is called plane of symmetry. The plane of symmetry may be regarded as the hypothetical plane passing through a molecule which bisects the molecule into two equal halves, which are just mirror images of each other.
The standard symbol for the plane of symmetry is sigma. The same symbol is also used for the reflection operation. There are three types of plane of symmetry. Number one, vertical plane of symmetry, sigma V. The plane of symmetry which is parallel to the principal axis or which contains the principal axis is called vertical plane of symmetry. Number two, horizontal plane of symmetry denoted by sigma H. The plane of symmetry which is perpendicular to the principal axis of symmetry is called horizontal plane of symmetry. Number three, dihedral plane of symmetry denoted by sigma D. The plane of symmetry which bisects the angle between two C2 axes of symmetry is called the dihedral plane of symmetry.
Here, in H2O molecule has two sigma V. First, sigma xz, it is the molecular plane. Second, sigma yz, it bisects the angle of HOH. Whereas PCl5 molecule contains 1 sigma H and 3 sigma V. Fourth is center of symmetry or inversion operation. If the reflection of all the atoms of a molecule through a point within the molecule produces an orientation which is indistinguishable from the initial one, it is called inversion operation, and that point is called center of symmetry. First and two are indistinguishable orientations, and thus Xe atom of XeF4 molecule is center of symmetry. Both inversion operations and center of symmetry are denoted by the symbol I.
Let's study the center of symmetry and its location for some molecules. In water molecule which is bent in shape, there is no center of symmetry. Opposite to that, in carbon dioxide molecule, the center of symmetry is present. The carbon dioxide molecule is linear in shape and the location of point of symmetry is at carbon atom. Also in the genome tetrafluoride XeF4 and SF6 which have square planar and octahedral in shape respectively, the center of symmetry is present and the location of point of symmetry is genome atom and sulfur atom respectively. Opposite to this, the molecule of methane which is tetrahedral, PCl5, triangular bipyramidal, BCl3 which is triangular planar, the center of symmetry is absent.
Let us now try to understand that where is the center of symmetry present or not present in some of the molecules. Let us first of all consider the water molecule, and as you are aware, the structure of water is bent like this, and there is no center of symmetry, and obviously there is no location of point of symmetry. Moving to the next molecule, which is carbon dioxide. Now, in the carbon dioxide molecule, as you are aware, the shape of carbon dioxide is linear and there will be a center of symmetry present, and that center of symmetry is this carbon atom. You can see when you look on this side or on this side, you have these symmetrical oxygen atoms, and that's why the point of symmetry is this carbon atom. Considering the next case, which is XeF4. Now, if we look for the structure of XeF4, XeF4 is a square planar molecule, and you know that all these fluorines and the xenon are in the same plane. Now, here also the center of symmetry is present, and that center of symmetry is this xenon atom. Now again you can see that through this center of symmetry, if you move this side you have a fluorine atom, if you move this side you again have a fluorine atom. Similarly, these two fluorine atoms, that is this one and this one, are also symmetrically placed. So you can clearly see in this particular case the xenon is the center of symmetry. Moving to the next example, which is SF6, that is sulfur hexafluoride, and you are already aware that the structure of sulfur hexafluoride is octahedral, whereby you have these 4 fluorines in one plane and one fluorine in the top and one on the bottom. So as a result, you have this octahedron which is there. Now here also, if you look, where is the center of symmetry? The center of symmetry is the sulfur, and how you can notice this? If you move equally on this side and this side, you find fluorine atoms. Similarly here and here again you have the fluorine atoms, and moving top and bottom again you have the fluorine atom. So this molecule has the center of symmetry, and the location of point of symmetry is the sulfur atom. Considering the next case, which is CH4. Now CH4, you are aware, because of the sp3 hybridization, the molecule is tetrahedral, that is it has this structure where this hydrogen is coming out of the plane, this hydrogen is going behind the plane, and these two hydrogens are in the plane. So looking at such a molecule, we see there is no center of symmetry, because if you consider that, let the carbon be center of symmetry, and if you move to this side for the hydrogen, there should have been a hydrogen here in the same plane or opposite, but then it is not there. Similarly, moving from this side to other side, there should have been hydrogen here, but that is also not the case. So clearly there is no center of symmetry, and obviously there is no location of point of symmetry in CH4 or in a tetrahedral molecule like this. Considering the next case, which is PCl5, that is phosphorus pentachloride molecule. The phosphorus pentachloride molecule, as you are aware, it is trigonal bipyramidal, that is these 3 chlorines are in the same plane, and there is one chlorine on the top and one chlorine on the bottom side. So in a molecule like this also, what you can see is, because of these positioning of these atoms, although this chlorine and this chlorine are symmetrically placed, but when you look at this particular chlorine, there should have been one chlorine here if it would have been a point of symmetry, but this is not the case. Similarly, for this chlorine there should have been another chlorine here, and for this chlorine there should have been another chlorine here, and all this is not true. And what we notice is that in this type of trigonal bipyramid molecule like PCl5, there is no symmetry element or point of symmetry which is there. Similarly, if we consider the case of BCl3, here also we'll find that there is no center of symmetry and obviously no location of point of symmetry. And how it can be understood? The BCl3, as you know, is a trigonal planar molecule, that is, all these three chlorine atoms along with this boron are in the same plane and the angle are 120 degrees. Now here, if we consider and think that yes, boron should be the point of symmetry or the center of symmetry, then what should have been there is, if we move equidistant on this side chlorine, similarly moving diagonally opposite, there should have been a chlorine atom, but this is not there. Rather, in place of this, it is here. And similarly for this chlorine atom, there should have been some chlorine atom here, which is again not the case. And similarly for this chlorine atom, there should have been a chlorine atom diagonally opposite, which is also not the case. So what we conclude is that in BCl3, there is no center of symmetry or location of point of symmetry.
In this table, presence of center of symmetry in various molecules can be seen. Now, last one is axis of improper rotation or improper rotation symmetry operation. If the rotation of a molecule about an axis through an axis by 360 degree divided by n, followed by reflection through a plane perpendicular to the axis produces an orientation which is indistinguishable from the initial one, it is called improper rotation symmetry, and the axis is called n-fold axis of improper rotation, Sn. Let us illustrate it taking the following example. In this example, the z-axis is S4 axis of improper rotation because 1 and 2 are equivalent orientations. Now we will study about the symmetry groups that are involved in various molecules. The complete set of symmetry operations that can be carried out on a molecule is called its symmetry group. The symmetry group of a molecule is determined by the symmetry elements possessed by it. The symmetry group is also called point group because, first, all the symmetry elements of a molecule intersect one another at a common point. Second, the position of this point is not shifted by any of the symmetry operations. Some common point groups along with the symmetry elements, an example, are given in the following table. Here we have some more symmetry groups: dihedral, tetrahedral, and octahedral. Now we will see symmetry groups in various metal carbonyls with the help of a table as shown.
Here we will study about the application of infrared spectroscopy in determining the symmetry of metal carbonyls. It is often possible to predict the symmetry of the arrangement of the carbonyl groups around the metal atom in a metal carbonyl from the number of carbonyl stretching bands that are observed in the IR spectrum. However, this task requires the adequate amount of judgment and proper experience in order to avoid the errors. This procedure consists of following steps. Number 1, several possible structures of the metal carbonyl under consideration are drawn. Number 2, the number of carbonyl stretching bands which are expected to appear in the IR spectrum is calculated from the symmetry of each structure with the help of physical and mathematical requirements. Number 3, experimental observations are then compared with the above predictions. The structures which disagree with the experimental observations are discarded. In favorable circumstances, there will be only one structure remaining. In this procedure, due regard must be given to the possibilities of bands being weak, or superimposed, and of course, the correct model must be among those considered. The reliability of this procedure can be enhanced appreciably if the behavior of approximate force constants and the relative intensities of the bands are also taken into account.
Let us illustrate the above procedure taking example of cis and trans isomers of metal carbonyls of the type Ml2CO4. The approximate forms of the carbonyl stretching vibrations and their IR activity for the cis and trans isomers of Ml2CO4, considering only the symmetry of the MCO4 portion, are given in the following figure. Both of these have the same vibrational frequency. For the cis isomer, all the four forms of the CO stretching vibrations are distant and can absorb IR radiations. On the other hand, for the trans isomer, two forms of CO stretching vibrations are equivalent and have the same frequency. These forms are IR active and absorb the same frequency of IR radiations, giving rise to a single absorption band. The other two forms of CO stretching vibrations are IR inactive because they do not lead to the change in the dipole moment of the molecule. For MO, PE, T3 whole twice CO4, two isomeric compounds have been isolated. One of these isomers has four absorption bands at 2016, 1915, 1900 and 1819 centimeter raised to the power minus 1, and thus it is certainly the cis isomer. On the other hand, the isomer exhibits only one strong absorption band at 1890 centimeter raised to the power minus 1, and thus it is trans isomer. It is obvious that the cis and trans isomers of the metal carbonyls of the type Ml2CO4 can be with the help of IR spectroscopy.
Let us recapitulate what we have learned in this module. In this module, we have studied the applications of infrared spectroscopy in determination of the symmetry of metal carbonyls. We have also discussed some important points that symmetry is a widely distributed properly in nature. Human body is symmetrical. The one half is just the mirror image of the other half. The symmetry element is a geometrical entity such as a point, a line or a plane, which are one or more symmetry operations can be carried out. Any action which leaves a molecule looking the same is called a symmetry operation. We have studied the 5 symmetry elements and 5 symmetry operations corresponding to them. The symmetry operations which produces an equivalent orientation is called an identity operation. If the operation of a molecule about an axis by 360 degree by n produces an orientation which is indistinguishable from the initial one, it is called rotation operation, and that axis is called n-fold axis of proper rotation, Cn. The hypothetical plane which bisects a molecule into two equal halves which are just mirror images of each other is called the plane of symmetry, denoted by sigma. If any line passing through a point within the molecule meets identical atoms on both the sides of the equal distances, it is called the point or center of symmetry, denoted by I. If the rotation of a molecule about an axis by 360 degree oblique n followed by reflection through a plane perpendicular to the axis produces an operation symmetry, and operation which is indistinguishable from the initial one, it is called improper operation symmetry operation, and that axis is called n-fold axis of improper rotation, that is Sn. The complete set of symmetry operations that can be carried out on a molecule is called its symmetry group or point group. The symmetry of orientation of the carbonyl group in this space in a metal carbonyl can be predicted on the basis of number of absorption bands in the IR spectrum.